Welcome to our discussion on securing artificial intelligence systems against modern threats. Today, we will explore how foundational cybersecurity practices blend with specialized defenses to protect complex machine learning environments. Understanding these defensive layers is highly practical for your professional career. When your organization wants to adopt a new intelligent chatbot or a predictive analytics tool, you will be the person tasked with evaluating whether that vendor is safe. Knowing exactly how to spot the difference between robust artificial intelligence, security, and superficial tech jargon will allow you to confidently approve safe deployments and block tools that could expose your corporate data. Let us start with foundational security controls. A major trap many professionals fall into is believing that intelligent systems require completely reinvented security framework. In reality, traditional security measures are the absolute bedrock of any trustworthy machine learning solution. Consider access controls and the concept of least privilege. Least privilege means giving an employee or a software program only the absolute minimum permissions required to perform a specific task. Imagine hiring a plumber to fix your kitchen sink. You let them into the kitchen, but you certainly do not give them the combination to your personal safe or the keys to your car. In our context, we must strictly limit who can view or alter the initial training data sets and the finalized model files. This tight restriction stops bad actors from stealing the intellectual property or silently corrupting the data, a destructive act known as poisoning. Crucially, you must expand these strict access rules outward to cover every single vendor and system involved in the entire supply chain. We must also apply rigorous controls over data confidentiality, minimization, and integrity. Minimization simply means gathering only the information you absolutely need and nothing extra. These practices protect personal privacy while engineers are sketching out their initial designs. Now, you might assume we should just scramble all the data with encryption to keep it safe. While encryption is perfect for information sitting idle on a hard drive or traveling across the internet, it presents a unique hurdle here. During the actual learning phase, the algorithm must be able to read the raw information in clear text to understand it. Because encryption is impractical during this specific phase, we rely heavily on data integrity checks. Integrity ensures the information has not been secretly tampered with, acting as a vital shield against poisoning attempts. Finally, we have security monitoring. Traditional alarms that watch the network perimeter are still necessary, but they must evolve into a broader concept called observability. Observability means looking deeply into the internal behavior of a system while it is running, using data signals called telemetry. Think of traditional monitoring as watching a building through an exterior security camera, whereas observability is like hooking up a heart rate monitor to see how the system is functioning internally. By blending standard network alerts with internal behavioral signals, you can catch an attacker who is trying to manipulate the system while it is actively processing real tasks. Next, we need to examine threat and vulnerability identification. In standard software development, IT teams use automated scanning tools to hunt for known programming mistakes. However, these conventional scanners fall remarkably short when dealing with artificial intelligence. These scanners are built to read explicit, step-by-step written instructions, but machine learning algorithms do not operate on readable lists of commands. Their logic is hidden deep within their mathematical architecture, their features, and their weights. Features are the specific data points the system pays attention to, and weights dictate how much mathematical importance the system gives to each of those points. Pointing a traditional scanner at an intelligent algorithm is like trying to use a spelling and grammar checker to evaluate the emotional depth of an abstract painting. It is simply the wrong tool. Despite this, traditional secure coding is completely necessary for all the supporting software that wraps around the core algorithm. The central brain needs a way to communicate with users, typically through a software bridge called an inference engine or an application programming interface wrapper. Think of the core algorithm as a massive amusement park roller coaster, and the surrounding software as the ticket booth, the waiting line, and the safety gates leading up to the ride. Those gates must be built securely. This involves rate limiting, which restricts how quickly someone can send requests so the system does not crash from an overload of traffic. It requires input validation to ensure incoming messages do not contain malicious computer commands, and it heavily relies on a principle called fail-close. Failing close means that if the system breaks down or loses power, it automatically locks all its electronic doors securely, rather than failing in an open, vulnerable state. Let us move on to a powerful defense mechanism called prompt templates. When users interact with a generative system, they provide instructions or questions called prompts. If users can type literally anything they want into the text box, clever attackers can use tricky language to bypass safety filters and hijack the system, a danger known as prompt injection. To combat this, developers use prompt templates as a mandatory pre-processing step. A template forces the user input into a highly structured, sanitized format before the central brain ever sees it. Imagine going to a government tax office to file a return. Instead of letting you walk in and hand the clerk a handwritten diary of your expenses, they force you to fill out a standardized form with specific numbered boxes. This standardization strips away confusing or dangerous language. As a bonus, because the machine receives information in a highly predictable format every single time, it actually operates faster and produces much more accurate results. Before looking at internal defenses, we must briefly mention adversarial testing. This is a proactive security measure where your own team deliberately acts like attackers. They actively throw confusing, tricky, or malicious data at the system to see exactly where it breaks. By discovering how the system gets confused during the safe testing phase, engineers can patch the weaknesses long before the product is released to the real world. Now we will explore two advanced techniques used to mathematically harden the algorithm itself. The first is called defensive distillation. Distillation is an elegant way to detect and guard against deceptive inputs. It involves training two completely separate systems. First, engineers build a massive, complex network called the teacher model, which learns from raw, messy training data. Once the teacher is highly accurate, engineers take its perfectly refined answers and use them to train a second, smaller system called the distilled model. This distilled model is what you actually deploy for daily use. Because it learned from pure, confident answers rather than chaotic raw data, the distilled version is incredibly resilient. Think of a professional musician who spends 20 years making terrible sounds before mastering the violin. When they finally teach a young student, they only show them the correct finger placements, completely omitting all their past mistakes and bad habits. The student learns a much smoother, more confident way to play and is far less easily distracted by bad sheet music. Our final concept is regularization. Regularization is a mathematical technique designed to prevent a flaw known as overfitting. Overfitting happens when a machine practically memorizes its training data rather than grasping the underlying broad logic. If a teenager just memorizes the exact sequence of turns to pass their neighborhood driving test, they will likely crash as soon as they encounter a detour or a new city. Regularization forces the system to generalize its understanding, making it adaptable to totally new situations. Crucially, regularization also acts as a brilliant security defense. Some sophisticated attackers try to map out a system by submitting thousands of tiny, microscopic variations in their data, trying to figure out exactly where the algorithm draws its strict boundary lines. By using regularization, engineers intentionally blur those rigid boundary lines. Making the internal decision rules slightly softer and less rigid makes it nearly impossible for attackers to successfully launch these inferential, probing attacks to reverse engineer the system. Let us recap the key takeaways from today. We learned that conventional security practices, like strict access rules and data integrity checks, are the absolute foundation of trustworthy artificial intelligence. We discovered that while traditional code scanners cannot read mathematical algorithms, rigorous secure coding is still mandatory for the software surrounding the core system. We examined how prompt templates clean up user input to block injection attacks. And finally, we explored how defensive distillation and regularization act as internal armor, blurring boundaries and refining logic to frustrate attackers. To ensure you are fully prepared for your certification, remember that all the important topics and concepts from this session are covered in the multiple choice questions on RooCloud.com. I strongly encourage you to solve the chapter-wise questions to reinforce your learning and test your understanding before we move on to the next session. Keep up the excellent work, and I will see you in the next session.